Hello everyone. So in the last class we have seen the theory of Lagrange's method. Now we will see how to do the problem. So find the general solution of the PDE minus yux plus xuy equal to 0. So as usual we can write the characteristic equation. So xt equal to minus y, yt equal to x and ut equal to 0. So our vector p, the p vector has the coordinates as a, b, c. So it is minus y, x, 0. Now we have p with us. Now we have to find two vectors p1 and p2 which should be independent of each other and such a way that they should be orthogonal to p. That is p dot p1 should be 0 and p dot p2 should be 0. So we can take any value for simplicity. Here I am choosing p1 as xy0 because I know the dot product here will be minus yx plus xy. Third coordinate is 0. So this p1 dot p is 0. And p2, since here third coordinate is 0 and first and 2 are non-zero. So as in p2 I am taking first and 2 as 0 and third coordinate is non-zero. And I am sure that p dot p2 will be 0. So that's why I am choosing p2 like this. 0 into y, x into 0, 0 into 1. So I have chosen p1 and also p1 and p2 are independent of each other because here first two coordinates are 0 and third is non-zero. Here third is 0 and first two are non-zero. So I am sure that p1 and p2 are independent. Also p dot p1 is 0, p dot p2 is 0. Now while choosing p1 and p2, one more thing you have to keep it in mind is that the p1 and p2 should also be exact. That is, their cross product should be 0. Del cross p1 and del cross p2 should be 0. So if you are not getting 0, you have to again adjust it p1 and p2 so that their cross is 0. So del cross p1, del cross, you may be knowing this is the determinant ijk, dou by dou x, dou by dou y, dou by dou u, and the coordinates are x, y, 0. So I into this is 0, here dou by dou u of y 0, j into dou by dou x of 0, dou by dou y of x is 0, k into dou by dou x of y is 0, dou by dou y of x is 0. So this is completely 0. So del cross p1 is 0. Similarly, del cross p2, you can check this here. Since this is a constant term, it will be definitely 0. So we have got two vectors which are exact. Since p1 and p2 are exact, there exists potential psi and phi whose gradient happens to be p1 and p2. So there exists psi and phi such that p1 is equal to del phi and p2 is p1 equal to del psi and p2 equal to del phi. So our aim is to find psi and phi. So we have p1 is xy0 is equal to del phi. So del phi is dou psi by dou x, dou psi by dou y, dou psi by dou u. Now comparing these terms, you can find the value of psi. Here it is very easy because dou psi by dou x is x. It means that in psi there should be a term containing x square by 2 because when you differentiate x square by 2 with respect to x, you will get x. Then dou psi by dou y is y. It means that it also should contain a term called y square by 2. Now dou psi by dou u is 0. It means that psi is independent of u. So in psi you need not take the term u. So I can write psi as x square plus y square by 2. And you verify whether this is correct. Because if I take psi like this, dou psi by dou x is x, dou psi by dou y is y, and dou psi by dou u is 0. So I have taken psi correctly. Now I have to find phi also. For phi I have p2 is 0, 0, 1. So 0, 0, 1 is equal to dou phi by dou x, dou phi by dou y, dou phi by dou u. So dou phi by dou x is 0 means phi is independent of x. So in phi you need not write any x term. Dou phi by dou y is 0 means phi is independent of y also. So in phi you need not write y also. Now dou phi by dou u is 1. It means that Phi should contain the term u, because when you differentiate u with respect to u, you will get 1. So phi should be the function u only. Now you can see all these conditions are satisfied. If you take phi as u, dou phi by dou x is 0, dou phi by dou y is 0, and dou phi by dou u is 1. So the general solution is a linear combination of these two. So it is a function of x square plus y square by 2 comma u equal to 0. Or you can write u as a function of x square plus y square by 2. So function of x square plus y square by 2 means it is a function of x square plus y square. As we know, constants we can remove, or we need not write the constant term. Okay, so u is an arbitrary function of x square plus y square. This is the general solution of the given PDE. So we found the general solution. Now suppose that an initial condition is also given. So the initial condition is given is u at x0 equal to sin x for x greater than 0. Now we have to incorporate this initial condition in this general solution. So this is the solution. So when I incorporate this condition, I have to put y equal to 0. So when y equal to 0, I am getting u as sin x. So I get sin x equal to g of x square. Sin x equal to g of x square. So I have to get the function g. For this I am putting x square equal to some theta. So I will get g of theta equal to x square is theta, so x is root of theta. So g of theta equal to sine of root theta. So I got the function g. G acts like this. G of theta is sine of root theta. It is just like g of x equal to sine of root x. So in this way g acts. Now I can substitute the value of g here. What is u? U is a function of x square plus y square. And what is g? G acts like this. G of theta is sine of root theta. So what will be our u? U in this case will be, u is a function of x square plus y square, and that function is sine. So u is equal to sine of root of x square plus y square. Okay, sine of root theta. So here I have written g of theta. Here you have to write g of x square plus y square. So g of theta is sine of root theta. So g of x square plus y square will be sine of root of x square plus y square. So u is equal to sine of root of x square plus y square is the required integral surface. This is the solution. So in this way you can do the problems. So only one problem is worked out in the textbook. So from the exercise I have done one more problem, that also we will see here. So consider this is given in the exercise. So we will see this problem now. So use the Lagrange method to find a solution of u of xy that solves the problem u ux plus uy equal to 1, and the initial condition given is u at 3x0 equal to minus x. Minus infinity less than x less than infinity. B part is show that this curve is contained in the solution surface. Means that this curve should lie in the surface. It means that this curve should satisfy the solution, whatever integral surface you are getting. One more part is there, C part is also there, that we will see later. Okay. So first we have this equation. We will write the characteristic curves. So the characteristic equation are xt equal to u, yt equal to 1 and ut equal to 1. Now we can write the vector p. P is the vector u11. Once I got p, my aim is to find two vectors p1 and p2 which are independent of each other and they are orthogonal to p. So I'm choosing p1 as 0, minus 1, 1 because this dot product u into 0, 0, 1 into minus 1 plus 1. So it is 0. Another p2 I am taking as minus 1, 0 u. So this, when I take dot product, minus u plus u, so it is 0. So p1 and p2 are orthogonal. Also they are independent because here first coordinate is 0, here second coordinate is 0. So they must be independent of each other. Also I have to verify whether they are exact. That is their cross, del cross p1. I have to check. Since it is a constant vector, it will be 0. Also I have to check with p2. p2 also I am taking minus 1, 0 u. So here you can see all those quantities are 0 here, k into. So this quantity is also 0. So p1 and p2 are exact. Hence I can find psi and phi such that p1 equal to del psi and p2 equal to del phi. Now here p1 is 0, minus 1, 1. So which is equal to dou psi by dou x, dou psi by dou y, dou psi by dou u. Now dou psi by dou x is 0, which implies psi is independent of x. Dou psi by dou y is minus 1, implies that psi should contain the term minus y. Dou psi by dou u is 1, implies psi should contain the term u. So I can take psi as minus y plus u. Similarly, p2 is minus 1, 0 u. So dou phi by, which is equal to dou phi by dou x, dou phi by dou y, dou phi by dou u. Dou phi by dou x equal to minus 1 implies phi should contain the term minus x. Dou phi by dou y equal to 0 means phi is independent of y. Dou phi by dou u equal to u implies that phi should contain the term u square by 2. So I can take phi as minus x plus u square by 2. Now you can check whether it satisfies this condition, whether del psi is 0, minus 1, 1 and del phi is minus 1, 0 u or not. Since these conditions are all satisfied, I can write the general solution as a arbitrary function f of minus y plus u, comma minus x plus u square by 2 equal to 0. So this is our general solution. I can also write it like this. Minus x plus u square by 2 is a function of g of minus y plus u. So from this I will get u square equal to 2x plus a function of u minus y. Now I will put the initial data. It is given u of 3x 0 equal to minus x. So I have to put y equal to 0. At that time u is minus x. So here I will get x square equal to 2 into x I have to replace with 3x. 3x plus g of y is 0 and u is minus x. G of minus x. So from here I got g of minus x is x square minus 6x. Now I have to get what is g of theta. So g of theta will be theta square plus 6 theta. Okay. Now I have, this is my solution. G of theta is theta square plus 6 theta. So what will be g of u minus v? So g of u minus v will be u minus y whole square plus 6 into u minus y. So I have to substitute here u square equal to 2x plus u minus y whole square plus 6 into u minus y. This is the solution. Now if required you can do further simplification and you can write u equal to some function of xy like this. So this is a required surface. Now our B part is we have to check whether the given characteristic curve lies on the integral surface. So if the characteristic curve lies on the integral surface, the coordinates of the characteristic curve should satisfy the integral surface. So here x is 3x, y is 2 and u is 4 minus 3x. Substitute here and check whether it satisfies or not. So it's a direct one. You can directly substitute the value and check whether it is correct or not. Now there is also a C part of this question and the problem is solve ux plus uy equal to 1 and the initial condition is u of 3x comma 2 equal to 4 minus 3x. Now this problem I did it in two ways. One, if this is asked as an independent problem, how to do that I have shown. And suppose that your A and B part, in the light of A and B part, we can do it directly because we know 3x, in the B part it is given 3x 2 4 minus 3x. Same one, 3x 2 4 minus 3x. It lies on the integral surface. Since this lies on the integral surface, for this also, if you take this as the initial condition, we will get the same integral surface. So from A, whatever integral surface we are getting, you will get the same thing. Now suppose that A and or suppose B is not asked, how to do C directly, that I have shown here. So if B is not there, from A we have the solution. PD is same, so the solution we can take from A. So we have the solution here. Now we have to put the initial condition. So when you put the initial condition, you have u square, so 4 minus 3x whole square equal to 2 into x you have to replace with 3x plus g of 4 minus 3x minus 2. So from this I got g of 2 minus 3x like this. Now I have to write what is g of theta. So I have put theta equal to 2 minus 3x. So from this I got what is x. I have simplified it. So I got g of theta equal to theta square plus 6 theta. So now I can write what is g of u minus y. So g of u minus y will be u minus y whole square plus 6 into u minus y. Now we can see this is same as the part A. So simplifying, you can see that this is same. Whatever u we got in A, the same surface we are getting. Okay, so it has a unique solution and the solution is given like this. Or what I told earlier, you can directly get it from B. Okay, from part B, you can directly write the solution like this. Okay, so Lagrange's method, that portion is over. Okay.